2.7, it's compound probability. This is the homework that goes along with it. And here are the answers to last night's homework. You're going to want to pause this and check your work. All right, I am going to go backwards to this screen. Okay. This is on in your notes. Probability of compound events. What this says is this. If we've got two events taking place, and I'm going to give you an example, flipping a coin and rolling a dice. So, if I say we are going to flip a coin and then roll a dice. Okay. An example of a problem like this would be, what is the probability that I get heads and then an even? Heads and then an even. Well, this is the rule. When you are doing heads and then an even, you need to take the two probabilities and multiply them. So I'm going to write it like this. Probability of heads times probability of an even. You're going to actually want to write that down. Now, let's think about a coin. What is the probability of getting heads on a coin? What is it, everybody? 1/2, 1 out of 2, times, what is the probability of getting an even number on a dice? 1/2, because it's 3 out of 6. And when I multiply that, I get 1/4. Now, that is two types of probability. On Friday, we learned about theoretical, which is just based on the number of outcomes, and experimental, which is based on something somebody did. Let me ask you a question. Is this problem that we just did an example of theoretical or experimental? It is theoretical because we just thought about a coin. 1 out of 2 is head, and on the dice, 3 out of 6 is even. We're just thinking about the number of outcomes, so it is theoretical. Now, the type that we are learning about today is dependent and independent. Independent. They do not affect each other. Dependent, one event affects the other. Let me ask you a question. Do you think flipping a coin and rolling a dice are independent, one does not affect the other, or dependent, one does affect the other? What do you think? Yes, they are independent. So that example of getting heads on a coin and an even on a dice is an example of theoretical and independent compound probability. On Friday, we only did simple probabilities, so there was nothing to affect. It was just one event. Now, let me make up another one here. How about I'm going to put everybody's name in this room in a hat. And then I want to pick a committee of 3 people. Okay, so all students' names, and then I want to pick a committee of 3 people. Now, let me count you guys. Well, let's just say there's 20. I'm making that. Pretend that there's 20 kids in this class. 20 kids. All right. What is the probability that I'm going to pick? Oh, and then we'll do this. 20 kids, and let's say that there are 14 girls and 6 boys. Let's again, what we're doing, we are picking a group of 3 students at random from a hat, and I want to find the probability that I'm going to pick a girl, and then a boy, and then a girl. And I'm making up these numbers as far as numbers of girls and boys. Okay? So, again, what am I going to do? I'm going to multiply all my probabilities. So it's a probability of a girl times probability of a boy, and then last but not least, the probability of a girl. Okay. Here's my kids in the hat. What is the probability that the first person I pick out of the hat is going to be a girl? Justin? 14 over 20. And I'm just going to leave it like that for now. 14 over 20. Now, I picked out a girl's name, and that name is sitting on the desk. Am I going to put that name back in the hat? No, because if I put it back in the hat, I could pull that same person, and is that going to give me a committee of 3? No, because I could pull that same person twice, and then I'm not going to have a committee of 3, right? So now that girl's name is sitting on the desk. Now, after I pick the girl, what's the probability that I'm going to get a boy? Yes, there are still 6 boys in the hat, but there are only 19 slips of paper left in the hat. Now, I put that boy's name here because he's already on the committee. What is the probability that the third person I pick is a girl? Lily. There are 13 girls left out of 18 kids in the hat. Now, I'm not going to stand here and do this mathematically because I really don't care that much. So I'm just going to use the calculator. And I get 91 out of 570. So that is the chance of us picking a girl, a boy, and a girl. Now, I have a question for you. Is this example theoretical or experimental? That is still theoretical because it is just based on numbers in the class. Now, is it dependent or independent? Lauren, this is dependent because these 2 probabilities change based on what happened in the first one. They depend on the first one. Do you see that? All right. What do you always do to the probabilities? Add, subtract, multiply, divide. You always multiply. Let's look at a couple examples. Here we go. You roll a pair of number cubes. Number cube is a dice. What is the probability of getting even numbers on both cubes? So what am I going to do to these 2 probabilities? Everybody, multiply. So we want the probability of an even times probability of an even. All right, on my first dice, what's the probability of getting an even number? Everybody. It's 3 out of 6, which is 1/2. Times, when I roll my second dice, what's 1/2? I multiply and I get 1/4. Or is that theoretical or experimental? Theoretical. Is it dependent or independent? Say again. Independent. It's theoretical and independent. The one dice does not know what you got on the other one. It doesn't matter. They are independent. All right. You take a 3-question true or false quiz. You guess on all the questions because I guess you didn't study. What is the probability that you will get a perfect score? Now you got to think about that. 3-question true false quiz. So probability of it being right times probability of it being right times probability of it being right. All right. Now, we don't know what the answer is, but it's true false. What's the probability that you're going to get that right? Which is 1/2. One of them is right and one is wrong. So 1 out of 2 is right, times 1 out of 2 is right, times 1 out of 2 is right. That's 1/8. So you got a 1 out of 8 chance that bad boys, that they are all right. Not so good. Is that theoretical or experimental? Theoretical. And is this dependent or independent? Dependent or independent? It's independent. All right. Now, the rest of these problems that we are going to go over are problems that are actually in your book. You do not need to write these down because you can see these examples again in your book if you want to. They're not on your yellow sheet. All right. Suppose you roll a red number cube and a blue number cube. What is the probability that you roll a 3 on the red and an even on the blue? So probability of a 3 and then an even. What's the probability of getting a 3 on the first number cube? Everybody. 1 out of 6. And what's the probability of getting an even on the second number cube? 3 out of 6 or 1/2. That will give you 1/12. Now, is this theoretical or experimental? Everybody. That is theoretical because it's just based on the outcomes. Are these dependent or independent? Everybody. Independent. Okay. I want you guys to try this one right now. You can just write it on your paper. Suppose you roll a red number cube and a blue number cube. What is the probability that you will roll a 5 on the red and a 1 or 2 on the blue? Just do that on a little slip of paper. Due to the two probabilities. Okay, so we want the probability of a 5 times probability of a 1 or a 2. So on the first dice, what is the probability of getting a 5? Let's see. 1/6 times. On the second dice, what's the probability of getting a 1 or a 2? Yep, 2 out of 6 is 1/3, which gives me 1/18. All right. In a word game, you choose a tile at random from a bag containing the letter tiles shown below. You replace, super important word, the first tile in the bag and then you choose again. What is the probability that you will choose? Oh, I don't know where these letters are. What? Oh, here we go. Okay. What is the probability you will choose an A and then an E? So the probability of an A times probability of an E. So there are 4 out of 15 that are A's. Now, you are going to look at that tile and then you are going to replace it. Put it back in the bag. What's the probability that the rest are E's? The next one's 3 out of 15. You end up with 4 out of 75. Again, this is theoretical and independent, because when you put that tile back, the first pick does not affect the second pick. So this is independent. All right. Last example. Suppose you choose a tile at random from the little tile shown in example 2 without replacing. So you are not going to put it back. What is the probability that you get an A and then an E? Well, probability of getting an A is still 4 out of 15. The probability of getting an E, I took that one A out and it is sitting on the table. So there are 3 E's, but only 14 tiles left. When you multiply this, you get 2 out of 35. What type of probability is that? This is dependent, because the first affects the second, because I don't put the tile back. All right, let me look at this one. Suppose a teacher must select 2 high school students. You know what? We already did this. This is exactly like the one we already